Welcome to Chapter 4 of the Graph Neural Network series. Today we explore graph attention networks, or GAT, which bring the powerful attention mechanism from transformers to graph-structured data. Instead of treating all neighbors equally, GAT learns to focus on the most relevant connections. This is inspired by how humans naturally pay more attention to important relationships than trivial ones. By the end of this chapter, you'll understand how attention works on graphs and be able to implement GAT models. Let's understand why attention matters for graphs. In GCN, all neighbors contribute equally based only on degree normalization. But is that realistic? Consider an academic citation network. A paper may cite dozens of others, yet only a handful are genuinely foundational to its contribution. GCN treats all 50 citations equally. GAT, in contrast, can learn that those foundational papers deserve more attention weight while peripheral citations get less. This adaptive weighting allows the model to focus on what matters. The key insight is that relationship importance often depends on the features involved, not just the graph structure. Before diving into GAT, let's quickly review self-attention from transformers. The attention formula computes a weighted sum of values, where weights are determined by query key similarity. Queries and keys are linear projections of input features. We compute attention as softmax of Q times K transpose, scaled by square root of dimension, then multiply by V. This lets each position attend to all other positions with learned importance weights. For graphs, we adapt this idea. Each node becomes a query attending to its neighbors as keys and values. The key modification is that we only attend to graph neighbors, not all nodes, preserving the local structure that makes graphs special. Now let's see exactly how GAT computes attention. For a pair of connected nodes I and J, we first transform their features through a shared weight matrix, W. Then we concatenate the transformed features. An attention vector, A, is applied to this concatenation, giving us a raw attention score. We apply leaky ray LU for nonlinearity, allowing both positive and negative scores with a small negative slope. Finally, we softmax across all neighbors of node I, ensuring attention weights sum to 1. The formula is alpha-ij equals softmax over all neighbors J of leaky ray LU of a transpose times the concatenation of W times HI and W times HJ. These learned weights determine how much each neighbor contributes. Just like in transformers, GAT uses multi-head attention to capture different types of relationships. With K heads, we run K independent attention mechanisms in parallel. Each head has its own weight matrix WK and attention vector AK, learning different patterns of neighbor importance. The outputs from all heads are concatenated. The final representation is the concatenation over all heads of the attention-weighted aggregation. For the final layer, we typically average instead of concatenate to maintain the output dimension. Why multiple heads? One head might learn to focus on structurally similar neighbors, while another focuses on feature-similar neighbors. This diversity leads to richer representations. Let's walk through the complete GAT layer architecture. Input features have dimension F, with n nodes giving us an n by F input matrix. First, we apply a linear transformation W to get n by F prime features. In parallel, we compute attention coefficients between all connected node pairs using the attention vector A. These coefficients are normalized by softmax. Dropout is applied both to input features and to attention coefficients during training for regularization. The weighted aggregation combines transformed neighbor features according to attention weights. An ELU activation introduces nonlinearity. ELU is preferred over ray LU for smoother gradients. For K-head attention, we maintain K parallel computations with dimension F prime per head, outputting K times F prime dimensions after concatenation. Let's directly compare GAT and GCN. Aggregation. GCN uses degree-normalized sum where weights are fixed by graph structure, while GAT uses attention-weighted sum where weights are learned from features. Neighbor weights. In GCN, a neighbor's weight depends only on degrees of source and target nodes. In GAT, Weights depend on the actual feature content of both nodes. Parameters. GCN has order f times f prime parameters per layer. GAT adds the attention vector, roughly 2 f prime additional parameters per head. Expressiveness. GCN treats all neighbors identically given the structure. GAT can assign different importance to structurally equivalent neighbors. Computation. GCN is faster since attention computation adds overhead, but GAT's expressiveness often leads to better performance on tasks where neighbor importance genuinely varies. GAT opens the door to even more powerful architectures, graph transformers. While GAT restricts attention to graph neighbors, graph transformers allow each node to attend to all other nodes, just like standard transformers. This requires positional encodings to inject graph structure information. Common choices include Laplacian eigenvectors or random walk features. Models like Graph GPS combine local message passing with global attention, getting the best of both worlds. Grapharmor from Microsoft Research adds structural encodings such as node centrality and shortest path bias, and won the 2021 Open Graph Benchmark Large-Scale Challenge on molecular property prediction. The main challenge is scalability. Full attention has O of n squared complexity, making it expensive for large graphs. Current research focuses on efficient approximations to enable graph transformers at scale. Let's look at GAT's performance on standard benchmarks. On Quora, GAT with 8 attention heads achieves around 83% accuracy, roughly 1 to 2% better than GCN's 81%. Sightseer shows a similar gain, around 72.5% against roughly 70% for GCN, while on PubMed, the two methods are effectively tied at 79%. But the numbers don't tell the whole story. Visualizing learned attention reveals interesting patterns. For some nodes, attention is nearly uniform across neighbors, suggesting all connections are equally valuable. For others, attention concentrates on 1 or 2 key neighbors. This adaptive behavior is exactly what we wanted. The model automatically determines when equal aggregation is appropriate and when focused attention helps. Training converges at a rate similar to GCN, with the attention weights settling into a stable pattern well before training ends. Let's summarize the key ideas from this chapter. GAT learns neighbor importance through attention, allowing variable weighting based on features. Attention is computed via a learnable vector applied to concatenated transformed features. Multi-head attention captures multiple relationship types in parallel. GAT is more expressive than GCN at the cost of additional computation. Graph transformers extend attention to full graphs with positional encodings. In our final chapter, we'll bring everything together with real-world applications. Node classification for paper categorization, graph classification for molecular property prediction, link prediction for recommendation systems, and more. We'll see how the concepts from all chapters combine to solve practical problems. See you there.